Hello and welcome to Cracking the Cryptic, and the bonus content continues. Simon's posted a video solving Dave Gorman's cryptic crossword. Dave Gorman is a comedian in the UK, and he has done some very good series, including Modern Life is Goodish on the TV. His crossword is more than goodish. Dave's become a cryptic crossword compiler just in the last few months, I think, and he's being published in The Independent, and his puzzle today is really good. Simon solves it in the video, very good solve as well, and I strongly recommend it if you have any interest in crosswords or comedians. Maybe that's more of a UK thing, I don't know. But if you're only interested in Sudoku, I think we've got a treat for you today. This is from Cam Dennis, and we've done a couple of his very innovative puzzles before. This one is using the concept of a 4x4 magic square. Cam has seen us doing puzzles involving magic squares recently, and he clearly feels a bit sorry for the 4x4 magic square, as we're always doing 3x3 ones. And he's come up with a way to incorporate it. Now, what I love about the grid here is that he's found a way. You would think that a 4x4 magic square, yeah, sure, it could sit in a Sudoku grid in some way, but it wouldn't be symmetrical. It would just have to be sitting somewhere. He's found a way of putting it in symmetrically by skewing it. Now, you're immediately saying, but surely a 4x4 magic square is from 1 to 16, and all the rows, columns, and diagonals add up to the same number. Well, that is exactly the sort of magic square we're talking about, but since the numbers 10 to 16 can't appear in a Sudoku grid, we subtract 9 from each of them. So it's like modulo 9 arithmetic, if you know that. So we are looking in the purple cells to have the numbers 1 to 9, and then 10 to 16 are in the magic square, but they appear in the puzzle as 1 to 7. From each of those, you have to subtract 9. And then the rest of the grid solves by normal Sudoku rules. So that's all it is. It's a classic Sudoku with one magic square constraint. And in the magic square, I'm just going to repeat it because I think it matters. The numbers 10 to 16 appear as the numbers 1 to 7. That's what we have. So do try it on the first link below the video. I'll put Simon's crossword link below that. And let's get cracking. Looking forward to this. So first of all, can we do any regular Sudoku? So there's a 9 in one of those two cells because of the 9s up here, and a 5 in one of those two, 6 in one of those two. There's not a lot of repeated digits in the givens, so there's not much we can even sketch in as pencil marks, and that is going to mean, rather unsurprisingly, that I'm going to have to start considering the maths involved in the magic square. Now, what does a row, column, or diagonal of a 4x4 magic square add up to? Well, it has to be a quarter of the numbers 1 to 16 added up. Now, I could do all the maths to add those up, but the simpler way, I think, to consider it is to take the kind of extreme pairs. 16 and 1 must add up to the same as 15 and 2, the numbers kind of inside them on the chain. And that must add up to the same as 14 and 3, etc., etc. There must be 8 of those pairs. So if we just take the sum of 2 of those pairs, and they always add up to 17, that's 34. And that must be the row or column sum. Now, I might have to use the word line, because obviously here they don't appear as rows or columns, they appear as diagonals in our grid. But each of the lines of this magic square adds up to 34, if you considered the numbers as 10 to 16. Now that means in our grid, we'll be taking chunks of 9 out of that, and our grid will have rows and columns of the magic square adding up to either 34 or 25, or 16, or 7. I'm subtracting 9 each time. Now 7, I don't think that's possible, because the minimum for a row of the magic square is 1, 2, 3, 4, which is 10. Oh my God, no. That's not a reasonable consideration. Because remember, We're taking 9. Yeah, this is we're taking 9s off, and this is a diagonal conformation. So 1, 2, 3, 4 is not the minimum. We could have, say, 1, 2, 1, 3 adding up to. Let me just put that in, and this must be possible, I think. So that could be a row. That adds up to 7, which was one of the numbers I listed, and 3 of those numbers could have 9 added. So we could be looking at 1, 10, 11, 12, which adds up to 34. Okay, so I can't rule out 7, which is annoying. So 7, 16, 25. I think I can rule out 34 because in this sort of grid, that would have to be 9, 8, 9, 8. And we can't have a repeated 9 and 8 in the purple squares. As I said, we're using the numbers 1 to 9 and then 1 to 7 again. And that only allows 1, 8 and 1, 9. So we can forget 34. It would be useful to forget 7. Let's see if that 1, 2, 1, 3. I think that's the only combination that could do this. Let's see if that can be eliminated. Look, none of these rows going towards the southeast can be 1, 2, 1, 3 because they all contain a different number. And the same is true for these rows going down here. The diagonals are obviously ruled out, and I don't think they mattered anyway because they would contain repeated numbers because they're straight once we get to this grid. Now, you can't put 1, 2, 1, 3 down there because one of the ones would have to be in box 8 with this other one. So actually, it was this diagonal is the only one where 1, 2, 1, 3 could appear. Let's just look across the middle. We've got 14 already there. So this would have to add up to 16 or 25. This is a diagonal of the magic square, but it's a row in our grid. Now to add up to 16 would need 2 1s. That's impossible in a row. So we could rule out 1. To add up, so it's now too much for 16. With a 2, it would have to be 25. With a 2 or 3, we would need a 9 or 8 to make it up to 25 across here. And as I just said, we've only got 1, 8 and 1, 9 in the purple squares, and they're already placed. Bam! So 1, 2, 1, 3, thank God, is impossible in this grid. Although that took some working out to be sure about that. And 5 already appears twice. Yeah, that's vital. So that cannot be a 5. This one can't be a 5. That allows us to actually place a 5 here. In fact, 4 now in this box must be in one of those two. But we've now established the whole point of that, and I hope this helps, was to establish that every row and column of this magic square adds up to 16 or 25. So looking across this diagonal again, we've now established that it is 25, and it's not using 2 and 9 or 3 and 8. And it can't be using, no, hang on, 14, yeah, plus 11. And it can't use 2 and 9 or 3 and 8. And it can't use 5 and 6. I think these must be 4 and 7, and we can tell which way round. Brilliant. So the diagonal of the magic square has got us a start. Now we've got 9 and 8 here. That's 17. In their row, in their line, let's call it a line, we need another 8. Can't be 5 and 3 because the 2 5s are already in. Could be 2 and 6 or 1 and 7. And it could be 4 and 4. That's so hard to remember, but the configuration of the square allows it. So that's not actually all that helpful. 2 and 6, 1 and 7, or 4 and 4. 1, 2, 6, 4, 7 there. 1, 2, 6, 4, 7 there. I might as well put them in now I've worked it out. And it can't be 7 there and 1 there, obviously. But I think the others are all possible. Right, let's try this one with the 2 5s. 10. Now this has to add to either 16 or 25, so we need another 6 or another 15. We can't have 15 because that has to be either 8, 7 or 9, 6. And we've used the 8 and 9 in the cells, in the purple cells. So this adds to 6. Can't be 5 and 1 because we've used the 5s. So it's 2 and 4. And look at that 4. Brilliant. 2 and 4. This now can't be 2 and 6. This can't be 4 and 4 as well. Yeah. Okay. Okay, what about this one? 13 plus 2 and 1 is possible for 6. Oh, hang on. I've got 3 up here. 8 plus 2 is 10, plus 4 is 14. This must be a 2 to be 16. Yeah, you can't get to 25. Ah, that's used up both 2s. This is now a 1. This is a 7. 7, 12, 13, and 3 to get to 16. Now, I was going to look at this. 13 plus, can't use 2 and 1. We've used up all the 2s, so we must go to 25. We need another 12 between these two cells. Can't be 7 and 5, because this sees both. Can't be 4 and 8, because this sees both of them. Oh, hang on. It can't be 9 and 3, because we've used the 9. Oh, it can be 6 and 6. God, I just cannot remember being allowed to use the same digits in the magic square. Right, and I think we can finish it now. This must be 13, 15. That's the second 1. 1, 8, 13. This is the second 3. And we've used 2 1s, 2 2s, 2 3s, 2 4s, 2 5s, 2 6s, 2 7s, an 8 and a 9. Yes. Now, I'm not even sure that I'm going to bother to work out which 9s you have to add to make this magic square work. I mean, I guess across the middle, that's already 16. You need another 18. I don't know. I mean, that might be a little bit complicated. That's a little bit of further maths for you afterwards to work out how this magic square works once you add the 9s. But this is the only way it can sit in this Sudoku grid. So I'm just going to carry on. Should be classic Sudoku from here. 4 I can see can go there, and I can finish off this box because of that 7. Now down the middle, yeah, column 5's easy to complete. That 9 is there. That's a 2, 4 pair. 3 and 8 to go in here, and we've got a 3 to tell us. I mean, I think this is looking fairly straightforward now, but what a what a clever conception of a puzzle, again, from Cam Dennis. I mean, I really like that. I mean, and it'll be entertaining if we still get held up here, which is quite possible. It might be a tricky Sudoku anyway. 9 there. So 9. I keep hitting the wrong key. Sorry. 8. 9 and 5 here. 9, 5. Just remembered my mouse because I'm a moron. Right. Okay, now the corner boxes are a bit harder to get some traction on. That can't be 9 anymore. 2 must be over here, and that's quite interesting. It puts 2 in column 2 down here somewhere. 8 is restricted to those 2. Oh no, this, okay, 4. 4 and 4 there. Yeah, it's fairly straightforward. Now 3 can't go there. Because of this 3 it can't go there. So 3's in one of those 2, which puts it in one of those 2, which is not resolved yet. 6. This is quite a constrained box, but not quite enough. So there is still some Sudoku to do here. Excellent. Well done, Cam. Where about 6? 6 here. 6 in box 1 has to be here, given the other 6s in the grid. And that's going to allow us to finish off 6s. Uniqueness tells me they can't be 2 and 3. In fact, that 7 tells me they can't be 2 and 3. That has to be 2 and 7 now, which can't be in this cell. Yeah, that's a naked single, right. So 3 goes in there. 2 is in one of those. which has used up both 2s in row 8 and 9. So we can take them out of those 2 cells and put the 2 in there. This is a naked 1. That puts 1 here. That fixes 3. 9 is now resolved. We've got 2, 5 pair there. 9 and 3 to finish row 7. That sorts out both pairs above. 5 and 1 in column 1. 3 there. We've got an 8, 5 pair at the top. 4, 7 here. 8. That's the last number there. Right, 2, 4 and 2, 5. And now 2 boxes to finish. 8 and 1. That's a 9. That's been available for a long time. 5 and 7. And there we go. That is Cam Dennis's rather brilliant 4x4 Magic Square Sudoku. I'm a bit annoyed actually that he didn't use 1, 2, 1, 3 as one of the rows, because I spent a long time working out why it wasn't possible, and I could just have jumped to the conclusion that each row and column added up to 16 and 25 and I'd still have got the right answer. But I think it's important to do it logically and correctly and to notice all the possibilities. Thanks very much for watching. I hope that was enjoyable for you, and not too... I mean, I dare say there is a danger that my explanation was poor enough that you weren't following what I was thinking, but I was trying to get it out of my head. Thanks for watching. Hope to see you again soon on Cracking the Cryptic. Bye for now.